In the previous lecture, we were able to derive Coulomb's equation from Gauss's law. Now we're going to do the opposite. We're going to derive Gauss's law from Coulomb's equation. So we're going to make the assumption that our electric charges are static point charges. And let's begin with case number 1, which happens to be the most simple case. So case number 1 deals with spherical surface enclosing a single point charge. So let's suppose we have a single stationary point charge given by Q. What is the magnitude of electric field at a distance r from the point charge as shown? So we want to calculate the magnitude of electric field on the following green region, on this green outline. Now, because we're dealing with a stationary point charge, we can use Coulomb's law, which states that the electric field is equal to the charge Q divided by 4 pi epsilon naught multiplied by r squared, where r is this distance. It's essentially the radius of our sphere. Now, let's begin by stating the electric flux. So the net electric flux for this particular case is equal to the closed integral of our dot product of our vector, our electric field vector, and our infinitely small area given by dA. Now, this is, by definition, what electric flux is. Now, we just said for this particular case, our electric field is given by this ratio. So we can replace this electric field with this entire equation. And that's exactly what we do. Now, notice our Q is a constant, the 4 pi epsilon naught is a constant, and our R is a fixed quantity. So that means R in this case is also a constant. So we can take this entire fraction and bring it outside of the integral. And that's exactly what we get. Now, if we evaluate this integral, we get this ratio multiplied by the surface area given by A. And because we're dealing with a spherical surface, that means the surface area is simply 4 pi multiplied by r squared. So we replace our A with 4 pi multiplied by r squared. So notice the 4's will cancel, the pi's will cancel, and the r squared will cancel. And all we're left with is the following. So we see that our electric flux for this particular case is equal to the closed integral of E dA equals our Q, the charge inside our region, divided by epsilon naught, our constant. So we were able to derive Gauss's law from Coulomb's law for case number 1 when we dealt with a spherical surface enclosing a single stationary point charge. Now, let's move on to case number 2, which is a slightly less simple case, slightly more complicated case. Let's suppose now, instead of examining a spherical region, let's examine an irregular surface enclosing that same static point charge. So earlier, we essentially used the following surface given by A1. Now we'd like to examine some other shape. Let's suppose it's given by the following red region. Let's call this surface A2. Now, notice the following important point. Notice that the same number of electric field lines pass through surface A1 as surface A2. Now, recall that the electric flux is directly proportional to the number of field lines passing through that region. Now, because the same number of electric field lines pass through region A1 as through region A2, that implies that the electric flux is equal to the closed integral EdA of A2, which is equal to the closed integral EdA of A1. And we know for this case, because A1 is simply this green circle, this green sphere, and in case 1, we were able to show that this this is equal to this, that implies this is equal to Q divided by epsilon naught. So once again, for case 2, we show that the closed integral EdA is equal to Q divided by epsilon naught for any irregular surface containing that single static point charge. So for any type of surface surrounding a single static point charge, we have the following result. So we showed case number 2 is true. And finally, let's go to the most complicated case, case number 3. Now suppose we have many charges in some irregular enclosed region of space. Let's suppose we have the following surface and we have many different types of charges within our surface, and let's choose one charge. So let's suppose we choose this charge, and this charge is given by charge Qi that produces its own field given by Ei. Now we know from case number 2, for any charge, for any single point charge inside the region, we have the following equation that we were able to show in case number 2. Now, by the superposition principle of vectors, specifically by the superposition principle for electric fields, we know that the total electric field is equal to the sum of the individual electric fields. Now, this implies that our electric flux for such a case is equal to the closed integral of the total electric field multiplied by dA. And this is equal to, from this result, we can replace our E with a summation symbol, and we get the following result. Now, if we actually evaluate this, we get the following result. The sum of all our charges divided by epsilon naught. Now, what exactly is the sum of all the charges? The sum of all the charges simply gives us the total charge that is enclosed within our region, within our surface. And so that means we can replace this numerator with simply Q enclosed. And so we see that our flux, electric flux, which is equal to this quantity, is equal to the Q enclosed divided by epsilon naught. So we showed that each case is true, and this basically means that we were able to derive Gauss's law from Coulomb's law for the case when we're dealing with static or stationary point charges.